This computer. All right, let me go shut the door real quick so we don't have people yelling in the hall. Okay, so for today, we looked at some additional information comparing and contrasting iOS to Android on top of what we talked about last class. So let's take a couple of minutes. Did we find anything interesting in doing that research that you want to point out?
I think 2 pages is a little short in describing iOS versus Android. If you
So
compare,
I should have made it a 10-page paper.
no, at least three and a half pages.
Okay, well, what were the highlights then for the 2 pages?
I mean, the first page itself, I got like explaining the, achievements of Android and iOS separately. And
Okay.
in another 1 page, I cannot describe everything from the like all the iOS 1 to 14 iOS OS.
Well, I don't need everything. I'm looking for the highlight reel. iOS versus Android. Did you discover anything in your research beyond what we talked about in class last time that compares the two to each other?
Yeah, actually, I mean, the revolution started for iOS from iOS 4, I guess. Yeah, from iOS 4, it started developing, improving OS very much better compared to previous versions. And for Android, I think it's from Android 5, 5.0, I guess.
Okay, and what made it so much better?
Oh, 1 minute.
One of the point I like is the most is considering the security and privacy is more in iOS rather than the Android. And but the latest versions of the Android, like the security patch 2017 and 18, from there on they are like increasing their security things and the privacy things uh, into more into more broad area.
Okay.
I think in Android, I think the API, introducing API was the biggest achievement for Android. And from there, for iOS, we have like it started previously for iOS 6. It was giving few default Google applications like Google Maps and YouTube, but then later on it decided to launch its own maps, which was filled with a lot of bugs, and it fired one of his employees for possible reasons because of those maps and bugs. So that's what I found in research.
Okay, so one of the things you kind of stumbled upon was, not necessarily, directly related to the operating systems themselves, but this is more of the big companies where Apple, and we kind of mentioned this last time, I think, where Apple and Google were relative, friends. They had people from the two companies on each other's boards, and once they started becoming direct competitors in the mobile operating system space, you started having more and more headbutting going on there. And like you just mentioned, iOS was relying on Google Maps for, up to that point. So all of a sudden they're relying on their number one competitor in the space to provide GPS mapping type stuff, where maybe that isn't the smartest idea. Well, Apple tried to make their own version of maps, and it just wasn't as good. And even to today, it's just not as good in my opinion. So Google Maps, for those of you who are iOS users, I'm guessing most of you still use Google Maps instead of Apple Maps. You might have a couple that use Apple Maps in here, but in general, I think Google Maps is still the more popular of the two applications. So kind of an interesting twist. Also in the early days of iOS, for instance, the very first version of iOS had YouTube as an application. This is before the App Store. So people were doing, they were digesting a lot of multimedia through their smartphones when that really wasn't something they had previously done. So you look at just the advent of iOS as an operating system with the first iPhone and the things that let you do on a smartphone that we take for granted today that just were not part of operating systems back then. Okay, so let's sort of leave it at that. Hopefully, going through this paper, you filled in a couple of gaps and kind of took yourself on a little voyage through the history of where how we got to where we are today. One of the reasons I like doing that is, many of you, this is going to be interesting. So as people go back and watch these recordings in the future, it's going to become more and more of a true statement. What I'm saying is, many of you were too young when the smartphones really started becoming a thing to kind of remember the earliest versions of some of these operating systems. Most of this audience is, in their, early-ish 20s or something like that. There's a few of us in the class, myself included, that are a bit more experienced than that. And we might remember those very first smartphones and the phones before that and the phones before that and the bag phones and all that stuff. So it's very interesting from a computer science perspective for us to kind of recognize how we got to where we are today, because there's a lot of things we take for granted on our smartphones today that our modern day ARM architecture and the operating systems that leverage it are delivering to us. All right, so this kind of takes you back on that voyage and catches you up. All right, so now I want to start talking about, let's see, let's actually talk about binary. All right, when I say binary representation of numbers, what am I talking about?
Zeros and ones.
Okay, so these are numeric values comprised of only zeros and ones. That is, binary is base 2. Humans are typically used to base 10, where all numeric values are comprised of 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we build our numbers in base 10 with the digits 0 through 9. We build our numbers in base 2 with the bits 0 through 1. We build our numbers with the bits 0 through 1. We build our numbers with the digits 0 through 9. Now, is there any difference in magnitude of a value? If I have the value 7 represented in decimal versus the number 7 represented in binary, are they both representing the same number? They both mean 7, correct? We're just kind of we have two different ways of expressing that value. That make sense? All right. So why do human beings express our numeric values in decimal, And why do computers express their numeric values in binary? What's the rationale for that? Okay, so your first part of your answer is it's easier for humans to go 0 to 9. Why is that? Why is it easier for us to do that? Well, is it? Isn't zeros and ones shorter?
Yeah, when you write 9, it's easier to read. I can say that.
Okay. Is it really easier to read, or have you just been doing it your whole life so it feels easier to read now? Because you look at zeros and ones, that looks scary, right? Okay. So now really, why do human beings do base 10? 10 fingers, 10 toes, right? You know, you think when you're a 2-year-old and you're first learning to count or something like that, you're counting on your fingers, right? You know, 1, 2, all that stuff, you know, just makes sense, right? You know, I do a lot of sci-fi reading, and it seems like all of the alien races in some of the sci-fi books, they all have 4 fingers instead of 5, so they use base 8. You know, it's just kind of that kind of thing. So effectively what we're saying is base 10 is compatible with human beings, okay? And then you mentioned that for binary, you know, you can use electrical signal is on, electrical signal is off. We say computers are digital things, ons and offs. So we would say binary is compatible with computers, right? That makes sense? Okay, so what other bases are common when humans are interacting with computers? Actually, I'm going to put this on its own slide. So based on your previous knowledge, when we're talking to computers, probably from the programming level down at the assembly level, which we're going to start talking about probably today, what other common bases do we run into besides decimal and binary?
Yes, obviously the language.
I'm not sure what you mean. Give me more.
Like scripting language, like programming language.
Okay, well, we're talking about number systems. So right now, I mean, when we say, yep. So when we say number systems, we are talking about how we can represent various magnitudes using a different, well, I already said represent. How we can represent various magnitudes.
Hexadecimal.
Okay, so i.e., whatever. Example, decimal 7 equals binary 111 equals, let's see, that's 1 in the, yeah, in octal equals 7 in octal equals, it'll be 7 in hex as well. All right, so it just so happens since these numbers are less than 8 and less than 16 that they are the same value. So our common number systems are octal as well as hexadecimal. So why octal and why hexadecimal? The answer is actually related to each other. why did we randomly, possibly, why did we randomly choose base 8 as a possible number system that is in some way compatible with computers? Similarly, why did we choose base 16, which is hexadecimal? So I'll just put it in, this is base 8. This is base 16. Why did we just choose? Why did we choose base 8? Let's start with that guy. Why not base 7 or base 9 or base 12? Why do we specifically choose base 8?
Is it because of buses in the early days of computing?
Okay, well, tell me more.
Like, the way connections were in buses, like you can only have 8 connections between two different components.
Okay. So I think what you're, so the starting point is that's not it. But I think what you're talking about is maybe parallel computing, when you have a connection between two things and it uses a parallel connection where it sends multiple things at once.
Yes.
Okay. We're actually kind of close there, but I don't think we're quite there yet. Let me ask you this. We talked about bits, right? I think Ishtiaq mentioned bits, so zeros and ones, right? What's the next level up when we talk about binary? After a bit, we talk about things in terms of bytes, right? What's a byte?
8 bits.
8 bits. Seen this number 8? 8 bits. So a byte is 8 bits long. So we can represent all possible byte values in 8 bits. Both parts of that say the same thing, right? So why octal then? Well, what are the possible values in base 8? That's actually a true statement. Let me ask you this. What are the possible, I'm going to use the correct name, octets. So these are digits in base 10. So when we build base 8 numbers, what are they built out of? What are the possible values that we use to create base 8 numbers?
0 to 7.
0 to 7. All right. So this is 0 to 7. So 0, 1, 2, 3, 4, 5, 6, 7. Right? All right. What's the smallest octal value? 0. What's the largest octal value? 7, right? If we were to write the octal values so all of the octal values can be fully represented in exactly 3 bits. And let me show you that on the next slide. Let me hide this. I want to check is who's on here? Nope. Wally Zuber must be deleting. Everybody here heard me offer to give him a ride last class. He just has to get up when I get up. Okay, so I'm just going to create another slide here. Octal values in binary. So a 0 is 0, 0, 0. A 1 is 0, 0, 1. A 2 is 0, 1, 0. A 3 is 0, 1, 1. A 4 is 1, 0, 0. And I'm going to create a I'll just duplicate this guy so the font doesn't get too small. A 5 is 101, a 6 is 110, a 7 is 111. All right, those are all of the octal values written in binary. And notice that we've used no more and no less than what can fully be described with 3 bits. So we can use exactly 3 bits to describe every single permutation of octal values. We could not describe every permutation of base 9 values with 3 bits, right? We'd have some leftover or some unused bit orderings. But I've used every permutation of 3 bits here to represent exactly the 8 unique octets of octal. Make sense? So that makes octal uniquely compatible with binary. We can represent all of the octets using 3 bits. That's convenient. All right. So based on that logic, we go down to the hexadecimal values. What's the next order up from a byte? So we have a bit, we have a byte. Less commonly do we use this next term. We have something called a word, right? It's not as cool. We don't use that as often. And even in some architectures, a word can mean some different things. We have words, we have double words. Typically, a word is 16 bits. A double word would be 32 bits. So a word is 2 bytes or 16 bits. All right. So the legal values, and they're called hex tests. Hex tests are, what are the legal hex tests in hexadecimal? 0 to 9, A to F, yep. All right, so legal hex tests are 0 to 9 and then A through F. So we represent all of our hexadecimal values using those 16 unique hex tests, right? Every value, every hextet in a hexadecimal number needs to take up exactly 1 space. That's why after we get past 9, we switch to A, because a 10 takes up 2 spaces, right? Now, how do you tell the difference between a 1, 0 and a 10? So we use an A to represent that. So the legal hextets are 0 to 9. Now, just like we had before, we can say all of the hextet values can be fully represented in exactly 4 bits. Let's steal this slide. So we're going to say hextet, and I'm going to rewrite the previous slide. This is actually the octets, the octet values. Understand that octet is to octal as digit is to decimal. Hextet is to hexadecimal as digit is to decimal. Our digits are 0 through 9. The octets are 0 through 7. The hextets are 0 through 9 and A through F. So we just have different names of talking about the symbols that make up these different number bases. If in your head you just want to think of them all as digits, that's okay. You know, these are the digits we use to make up a hexadecimal number, an octal number, or a decimal number. Human beings are used to that word digits, but in actuality, formally speaking, the things we use to build octal numbers are technically called octets. The things we use to build hexadecimal numbers are technically called hextets. All right. So the hextet values in binary can be represented in 4 bits. So 0 is 0, 0, 0. 1 is 0, 0, 0, 1. 2 is 0, 0, 1, 0. 3 is 0, 0, 1, 1. 4 is 0, 1, 0, 0. 5 is 0, 1, 0, 1. 6 is 0, 1, 1, 0. 7 is 0, 1, 1, 1. 8 is 1, 0, 0, 0. 9 is 1, 0, 0, 1. 10 is 1, 0, 1, 0. 11 is 1, 0, 1, 1. 12 is 1, 1, 0, 0. 13, and really, actually, we should say A, right? And this is B, C, D is 1, 1, 0, 1. E is 1, 1, 1, 0. Well, I don't know. I'll just put the F on this the same one rather than having a whole nother column. F is 1, 1, 1, 1. So notice we fully can represent all of the hextet values using 4 bits. No more, no less, right? 4 bits is perfectly compatible with all of the hextet values for hexadecimal numbers. Anybody know what 4 bits is called in computing? We sort of kind of skip something between bit and byte. A bit is a single 0 or 1. A byte is 8 zeros and ones. What's 4 zeros and ones? Called a nibble. It's called a nibble. More of a trivia type thing. Very rarely, modernly, will you hear that word nibble. Similarly, with high-level programming languages, you almost never use a primitive type short. For example, they still exist. They came from the C programming language. We're still there in C++. We're still there in Java. We're still there in C#. We're still there in Swift. The short data type, which is a signed 16-bit value, used to be meaningful to us when we were trying to save memory, when memory used to be expensive. Now, if you're going to store a signed number in Java, you just put it inside an int. Move on with life. Who cares about the memory you might be wasting? We have lots of it. All right, so today, this kind of is similar to that, our previous paper on, well, most of our previous things, is I want to fill in some of the blanks from the history of our computer architecture stuff, because as technologists, especially as master's students in a computer science program, we want to have a full understanding of the various foundations that the current state of technology is built on top of. Because all those things are still there, right? Day one of computers, bits existed, right? You talked about digital logic, ons and offs, zeros and ones, electrical signals, things like that. That same thing is the foundation of all of our computers today, isn't it? You know, we're starting to maybe move towards this idea of quantum computing, which adds a third state, actually. So that's going to probably throw a, pun intended, a spin onto the way we teach computer science. If you ever look into quantum computing, instead of on, off, there's 3 states. There's on, off, and something called spin, third state. We're not going to get into that in here, but more just, this is the way things work type thing. But in any case, things really haven't changed with computers foundationally. We've just put layers on top of the things that have been there. And really the stuff we're talking about right now, the idea of octal and the idea of hexadecimal, they've been here for a long, long time, right? Now, if you were to make a guess, back to this slide, if base 8 is popular because it can be fully represented in 3 bits, and base 16 is popular because it can be fully represented in 4 bits, what base would be the next popular one potentially because it can be fully represented in 5 bits? What base can be fully represented in 5 bits? Yep, base 32. What might be the next popular base in computing? And we're already used to base 32-bit processors, even 64-bit processors, things like that. So this isn't some random number that we've never heard of before. But we can say 32, well, let's say base 32, because the entire, and it has a name, but I don't know what the name is. I don't know what base 32 would be called. Let's look it up real quick. What is base 32 called? The base 32 numeral system, that's it. No, it doesn't show up on the first couple of Google search things, so maybe we don't have a name for it yet, but I'm sure there's some sort of mathematical name for radix in math. It's called a radix 32. So legal values are 0 through 9, then A through most of the alphabet, wherever letter 22 is in the alphabet to represent that. But base 32, because the entire base 32 element representation system can be held in exactly 5 bits. Then we might ask on here, will base 64 ever be a thing? What do you think? Base 32, we can say, well, maybe that, well, let's back up for a minute. Let me ask you a different question first. Will base 32 ever be a thing? We've just shown that it could be a thing, right? Because we can fully represent all of the components that it takes to build base 32 numbers using 5 bits. That would be 0 through 9, and then A through whatever number 22 in the alphabet is. Doesn't matter, some letter in the alphabet, late in the alphabet, right? Maybe W, whatever it is. All right, so 32 is at least possible. All right, so will base 32 ever be needed? Maybe. Why do we need base 16 over base 8? Why did we add hexadecimal? What is having the ability to represent values in base 16 over values in base 8 do for us? What's the benefit of that?
More number of bits.
Okay, why would having more bits be quote better?
Well, I think circling back to the class we're in, a bit representation. So we went from 8-bit to 16-bit. So that's why we got hexadecimal, and base 32 would be optimal for 32-bit representation, I think.
All right, so why is hexadecimal, what does hexadecimal let us do that base 8 struggles with? Let's say that. Why didn't we just stop at base 8? Or we could even roll back one more question and say, why did we even use base 8? Why did we just use base 2 and just have all the zeros and ones? Why did we need base 8? And why did we need base 16? Why might we need base 32?
It's very limited.
Tell me what you mean by limited.
I mean, more instructions are coming up every day. So we need more bits to actually incorporate more data.
Okay. You said two different things there. You said more instructions are coming out every day. When you talk about instructions, are you saying the things that a CPU knows how to do?
Yep.
Okay. Let me ask you this question. What is the largest decimal value that a 16-bit number can represent? Is what we're trying. The question I'm asking here is you said that new instructions come out every single time, every single day, let's say. I don't know if that's true, but once upon a time that probably was true when they were first working on processors. So then the follow-up question is how many unique instructions are there on processors today? I don't know the answer to that, but the answer to the next question is going to give us a pretty good idea of why the number of instructions is likely not the culprit here. So if I'm dealing with a base 16 number, what is the largest decimal value I can represent in 16 bits?
15.
Well, 15 is the largest hextet, individual hextet of a hexadecimal number. I'm saying if I give you 16 bits, 16 bits of address space, what is the largest decimal value I can fit in 16 bits?
That's pretty big.
Okay, well, how do you give me the exact answer? You could tell me how to calculate it if you want. 2 to the 16th power, so 65,536, right? It's a calculator inside my head. I've said that number a couple of times. All right, so if we're dealing with a signed number, it's 0 to 65,535. If it's an unsigned number, it's negative 32,768 to positive 32,767. Bottom line is we have 65,536 unique, to your point, unique instructions that we could represent using a 16-bit value. Do you think that our modern day processors have 65,536 unique magic tricks that they know how to do, or do you think we are nowhere close to that in reality? Okay, we're not even in the same ballpark, right? You know, modern day processors, you know, they might have several hundred magic tricks, most of which don't get used very often, but we're nowhere near 65,536 unique magic tricks. Okay. So let's go back then and ask the same question. Why did we add hexadecimal on top of base 8? Or you can similarly ask the question, why did we add base 8 on top of base 2? Why didn't we just stop at base 2 and say, hey, this is good enough? Because at this point, we're completely compatible with computers, right? Ons, offs, zeros, and ones. We don't need anything more than binary. Computers love it. So what's the advantage of base 8 and then the advantage of base 16 and further the advantage of base 32 if we ever find ourselves in a situation where we need to represent that? From a human being's perspective, what's the advantage of hexadecimal, base 16, versus binary?
Is it regarding this free space we can utilize?
Maybe. So you were asking a question about from a broad perspective. Go ahead, finish your question. Okay. No, I'm thinking more broad. Like the right down at the architecture level. That's what we're focusing on in here instead of you know, because architecture comes before all that other stuff. All that other stuff relies on the architecture, right? So let me ask maybe the question in a different way. When do you, when you're using a computer, you're writing software, when do you see hexadecimal values? What's a common occurrence when you might visually see a hexadecimal value? So here, let me come out here. I'll do a, do I already have a, yeah. We'll just write a quick little program. It's actually, CCC is not a thing on here. It's an Apple thing. If I were to run this, in fact, I want to make sure I can show it to you. Okay, good. I already have a way to show it to you here. I'll go ahead and do the same thing I did before. All right, so I'm writing a program here. I'm defining a variable named A, of type integer, putting a 5 in there, and then I'm going to go ahead and print out the address of A. Okay, so GCC test that, and then so we get crazy looking hexadecimal value, right? There's a number made up of all of representations of all the hex tests, or many of the hex tests. We got some F's in there. I see a D. We got a 7, a 1, a 3, a 9, a 4. Okay. Now, what is this value in decimal? I'm not asking you to actually convert it, but is it fair to say that that's a really, really big value in decimal? As human beings, we like decimal, right? Okay, we like decimal values. So if we were having to count that value, if we were having to say that value in decimal, we probably would have to take our time to even pronounce it, right? Once we get past millions and billions, we start needing to do Google searches to look up quintillions and quadrillions and septillions, all that stuff. So big number, right? Okay, Now, if I was having to represent this in binary, it would look even scarier, right? Whole bunch of zeros and ones. Okay. In fact, how many zeros and ones would this be? This would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 times 4, because there's 4 bits per thing. So that's a 48-bit memory address. Right? We just talked about a few minutes ago that the reason we use hexadecimal base 16 is because we can represent all of the individual hex tests in 4 bits, right? So that means if we were to write this in binary, we have 4 bits, followed by 4 bits, followed by 4 bits, followed by 4 bits, so on and so forth. So it happens to be that we have a 48-bit memory address here that I'm running Ubuntu Linux 64-bit. So their memory address space they've chosen is 48 bits. All right. Why 48 bits in this example? And you can assume an operating system has a 32-bit address space. Maybe that would have come before some of these. So when we say 32 bits, or we say in this case 48 bits, what do we use address space for? What's the purpose of having a memory address? Okay, so just like in real life, when we think about the address of our apartment, or the address of our house, whatever, is your address the same address as somebody down the street? Or do all addresses need to be unique? They're unique so that people can find you, or when Amazon's delivering your package, they can find you and they can also find the person down the street, right? So addresses need to be unique. So if we have, like we just saw with Ubuntu, if we have a 48-bit address, how many unique addresses are there in 48 bits? Yeah, well, the actual math is 2 to the 48, right? 2 to the 48. So there are 2 to the 48th power. So again, I don't know if, can I read that? That's thousands, that's millions, that's billions. 281 trillion, 474 billion, 976 million, 710,656. That's the number of unique memory addresses that we can represent in 48 bits. Okay, so if we were storing something that was the whatever the exact size, let's say all the houses in our computer memory were all the same size, we can have that many houses, 281 trillion, 281.47 trillion houses that could be uniquely addressed. So the question we would ask ourselves is, do we, when we have our computer running with the operating system going and all of our user applications running, do we need to remember the location of more than 281 trillion places at any one point in time? Because a computer program can request some memory and then it can give that memory back when it's done using it. So the real question is, do we need more than 281 trillion unique buckets of memory to remember all the things we might need to remember at any point in time while we're using our computer? We don't necessarily know, but that sounds like a pretty big number, right? So maybe we don't need to remember that many things at any point in time. So maybe 48 bits is enough, right? If we roll it back a little bit, say, well, was 32 bits enough? Well, 32 bits let us store 4.3 billion things at once. Still a lot, but now maybe we're getting more into the realm of reasonable, something like that. If I asked any of you to remember, to memorize 4.3 billion numbers, could you do it? We wouldn't want to. So good thing for us, because we know how the number system works, is we can calculate values. We don't have to remember the number 65,536 like I pulled out of air today, right? We can say, oh, well, that is just 2 to the 16th power. And I can mathematically calculate that 2 times 2 times 2 times 2 times 2, whatever, and get my final answer. All right. So these are the unique. So if we think of our computer like a town or a city or a state, whatever, you know, fill it up, and we think of all the houses living on one big long street. All right, because in real life, our memory addresses, our addresses in real life are much more complex, aren't they? You know, you have a street address, you have a, well, you have a number, you have a street, you have a city, you have a state, you have a country, you know, you have all these things that, you know, ultimately get you to your exact place that it's going. In a computer, all of our houses, all the addresses are in one big long street. Okay, whether we're dealing with a mobile device or we're dealing with a desktop computer, doesn't matter. System memory is just a big hardware-based array, indexed from bucket 0 to bucket, in this case, 4,294,967, 4,294,967,295. 0 to that. Those are the legal buckets of the array that is the unique memory addresses that exist in a 32-bit memory system. Okay, so depending on how much RAM we have, we probably don't need to represent that many things, but maybe, right? So if we have, let's see, you know, a computer with a lot of memory today might have 64 gigabytes of memory, something like that. So if we have 64 gigabytes of memory, let's actually do this on a slide. How many unique addresses do we need? If we have 64 gigabytes of RAM in our computer, which we could all admit is that's a lot of RAM in a personal computer. There are servers out there that have more memory than that, but most of us do not have a personal computer with 64 gigs of RAM in it yet, right? 32 is becoming more and more common. 16 is pretty common. 8 is no longer entertaining, all right? But 64 is possible. My computer here has 64 gigs of RAM in it. I built it that way because I emulate a lot of operating systems and stuff on here. But regardless, let's just say 64 gigabytes is our top for what a consumer computer might have in it right now, or a prosumer computer might have in it right now. So if we have 64 gigabytes of RAM in our computer, and each house in memory is of size 32 bits, 4 bytes. That means I'm just using that as a default value. So whatever operating system we're running uses what's called a 4-byte block size, let's say, which means that every one of those places in memory can hold 32 bits or can hold 4 bytes. Let's just say that's the case. That means if I have, so what is the largest amount of RAM that can be supported by a 48-bit memory system like Ubuntu 64-bit. I'm going to put a year in there in case somebody looks at these slides in the future. So this is 2021. Well, that is 2 to the 48th unique memory addresses. If each of those is 4 bytes, that is 2 to the 48th, which is this giant number. I'll put this in parentheses. Times 4, that's the total number of bytes. Divided by 1024, that's kilobytes. Divided by 1024 is megabytes. Divided by 1024 is gigabytes. Divided by 1024 is terabytes. So our max supported system RAM is 1,024 terabytes. We're not there yet, right? So I said my computer here is running 64 gigs of RAM, which we're going to say is a lot. And if I were running Ubuntu Linux on my computer, which we just saw uses a 48-bit memory address, or at the very least, that's what it exposes to a user address space. I just ran a C program and I printed out the memory address of this random integer 5. You know, I stored an integer somewhere in memory. I told the program to print out where in memory it stored that, give me the address, and it gave it to me as a 48-bit value. So evidence seems to suggest that in 2021, Ubuntu is Ubuntu Linux, which is built on top of Debian Linux, is exposing a 42-bit user address space. All right, this isn't an operating systems class, so we don't need to dive much deeper to find out if there's a, you know, maybe the operating system does some kind of segmented memory where it, you know, 48 bits for some stuff and more for something else. We'll just operate off of this 48-bit number to support the math, right? This goes back to what I was talking about a few minutes ago. We don't need to memorize all these things. We just do the math, right? Now, I realize that as you're going through this, and you're probably going to want to go back through this video for many of you a lot slower, right? Because I'm kind of doing this math here pretty quick. But I think once you start going through it, you start seeing the exact same patterns pop up. It's 2 to some power, right? Times the amount of crap you're storing at that particular place. So what did we do here? We said 2 to the 48th power. That's the number of unique memory addresses. If we have 4 bytes that we can store in each of those, I'm just making up a number. So if we're pretending like this is a big plot of land, each house is of size 4 bytes in my little made up world right now, okay? Depends on the operating system and what file system management thing it uses. It decides what's the size of a house. What's the maximum size of a house? I'm just gonna choose 4 bytes out of the blue here. So that means that we can store 1,024 terabytes. That operating system that follows the rules I just dictated here can support up to 1,024 terabytes or 1 exabyte of memory. That's the next number system up, an exabyte. It is, right? What comes after terabyte? I think it's an exabyte. I don't want to lie to you. What comes after terabyte? Oh, petabyte. Exabyte's the next one. Petabyte. Or 1 PB. Petabyte. All right. Fast forward a couple of years, we're probably going to be talking about petabytes and things and stuff like that. But right now, the cool kid is terabyte, right? You go out and buy a hard drive, you know, some giant hard drive, you can get like 6 and 8 terabyte hard drives. We're still in that low end of the, you know, we're below 10 of those. So we're not up in that 1,024 range yet, but it's possible. All right. So again, this idea is that when we're starting to talk about these different numbers, these numbering systems, all we're doing is we're trying to represent the number of unique things. All right, so we kind of review what we've talked about today so far. We talked about representing numbers in binary. We asked why. You know, we said that, oh, it's because that's convenient for computers. 0s and 1s are something computers can conveniently work with. Now, why do we use base 10 as humans? Because 0 through 9 are values that humans can conveniently work with. Our goal here is to somehow create a way for human beings to communicate with computers. So we need some stuff in the middle, okay? We picked out a couple of other bases that happen to be compatible with this goal. That's binary and hexadecimal, or I'm sorry, octal and hexadecimal, because they can fully be represented in 3 and 4 bits. Those number system values, okay? Base 4 could be fully represented in 2 bits, right? 0, 0, 0, 1, 1, 0, 1, 1. Those are the 4 unique things that could be represented in base 4. All right. Yeah. So we build our numbers with digits 0 through 9 as human beings, and now we need to find a way to be compatible. So now we start thinking about, well, what things do we need to do inside of a computer? One of the things we need to do inside of a computer is remember stuff. And we want to remember a lot of stuff. So some stuff we want to have is like long-term memory. That's the stuff that goes on your hard drive, right? So we expect that to be our biggest chunk of stuff that we can store. But then after that, we rely on system memory. That's kind of our real time. If somebody comes up and asks you what your name is, you kind of zip into your mind real quick and pull that piece of information, hopefully fairly quickly, right? So that's the real life version of system memory for us. And we're going to say that this particular, we're going to say that we want to have fast memory for that. And as long as it's cost effective, we'd like to have a lot of memory for that. You know, it makes us better at Jeopardy, right? The more pieces of information we have stored, the more things we can recall quickly. And you know, then you have the timing for the buzzer, how quickly you can buzz in. All right, makes sense? So I like trying to connect this stuff back to real life because it's not as complicated as it sounds like it is. It's just intimidating because we're talking about zeros and ones and octal and hexadecimal, and that's all scary and stuff. And then we go over here and we look at this guy and we're like, I can't read that, right? Just at a glance, we know that is a gigantic decimal number, correct? But do you think that this number right here has a smaller footprint than the decimal equivalent of it would be? So if I copy this value, let's see. Let's come up here and I'll do hex to decimal. Enter the hexadecimal number. So there's the conversion. So here's that number in decimal. Is the decimal number longer than the hexadecimal number? It is. Is the binary number even longer than the decimal number, which is even longer than the hexadecimal number? Okay, so let me ask you this. Is it a fair thing to say that if I were storing this magnitude of value, for human beings, we would read it this way, right? So I mean, what is this? It's thousands, millions, billions, trillions. This is 140 trillion, 733 billion, 521 million, 886,580. Big number, right? Not infinity, but big number. We can read it. Okay, I'm pretty proud of myself, actually. I was able to read the number. All right, but we're going to say, you know what? If I am trying to express this value to somebody else in the most compact form possible, this is more compact than this, which is even more compact than this if I was talking directly to the computer. Does that make sense? So sometimes this number that I have highlighted, this number, and this number all represent the identical magnitude. They all mean the same thing. That number has a value, right? It's all the same number. We're just representing it three different ways. Okay, just like many of you in class speak more than one language. Okay, so you have the word hello. In English, you might have it in Hindi, you might have it in Telugu. I think we have some Hyderabadi students in here, but whatever, that same word might be a different word in these different languages, but it still means the same thing. Make sense? Same things going on here. This is the word hello. This is the word hello. This is the word hello. Pick your poison, how you want to represent it, but generally as human beings go, if we can store something, if we can say hello in one syllable versus 2 or 3 syllables, we might prefer that. Something like that. It feels more efficient. Okay? So this is the reason why we might choose larger bases as long as they're compatible with binary. We chose octal because octal is compatible with 3-bit binary. We chose hexadecimal because hexadecimal is compatible with 4-bit binary. We would choose, if we needed to jump up another level, we would choose base 32 because it's compatible with 5-bit binary. Okay, what's the next guy on the list? Base 64, okay, which we would say is compatible with 6-bit binary. That's true, but why would we never use, well, let's just go with never. Based on our current understanding, let me just make sure we fill in the blanks here as I'm saying this stuff out loud. So why do we add hexadecimal on top of base 8? You can say the larger the base, the smaller the footprint for very large values. Make sense? It's a compression thing. It's a way to represent the value thing. You know, I'll say example from class was the English word hello spoken in different languages might have different lengths, but they all mean hello. Make sense? Okay. And generally, if we can store things in a smaller footprint, that seems like a good thing. Okay. So base 32, we can ask, will that ever be a thing? Well, we can say maybe. Maybe if we need to represent even more unique things in memory, as this can be fully well, I already say it above there. Will base 64 ever be a thing? Why or why not? What do you think?
Well, if you talk about the efficiency, starts going very, very low.
Okay. What are the legal, whatever the equivalent of digits are in base 32? What are the legal base 32-its? It would be 0 through 9, and then what? If we had base 64, we need 64 unique chars. So we'd have 0 through 9. We have A through Z, right?
Yeah.
So we have 26, 36. That gets us to base 36.
Yeah.
Ruh-roh. I need base 64. Where do we go from here?
We can use special characters.
We could use special characters, but we'd have to now invent update the standard, right? Because right now the hexadecimal standard, because of course, everybody on earth likes English, and the English alphabet, well, that's the way Americans think, right? Everybody likes English. So we have 26 characters in the English alphabet. We have 10 unique digits in base 10, which all humans can agree that's the most convenient, right? So human beings agree with that. Okay, Americans like the 26 character alphabet. So that means we can support up to base 36 using our current way of doing things. Like you said, you know, we could start using special characters, question marks, exclamation points, commas, things like that, to represent more of those unique values as long as it's one character big. We could pull it off. If you play some of those games on smartphone games, iPhone, Android has several of them. like, I don't know, AFK warrior or something like that, where it's like tap warrior. You just sit there and tap the screen, you do a bunch of damage. It starts representing large values as you're doing damage using, it just wraps around the alphabet. It just uses like an AA, which actually now is 2 characters long, but the assumption is if you have an A next to an A, that means one big AA. It's a single character thing. Looks complex, looks scary. People who are playing that game, they don't understand different bases like we do. Okay, so they just kind of go with it. They're not trying to convert it to decimal. They just know that if they did, 1, 2, AA, BB, CC damage, they did a lot of damage. Okay, but for us, we might say we really need to have a formal definition of how do I represent bases above 36, because now we've run out of the digits that are legal. We've run out of the alphabet that we historically use. We need a new alphabet or an extended alphabet. Okay, the joke I historically make in class for the sci-fi geeks is you could use Klingon, right? If you follow Star Trek, a little bit dated, but there's a race of aliens in the show Star Trek called the Klingons, and there actually is a Klingon language. If you've seen the TV show Big Bang Theory, one of the funny things in there is all the geeks in it know how to speak Klingon, and they'll speak it to each other and stuff like that. But we've looked it up. There is a Klingon language that I'm sure some nerds have designed online. It does exist, but there's only 22 characters. So we actually take a step backwards actually with Klingon. We can only represent up to base 32 if we go with Klingon. All right. But the good news for us is we can say maybe, but we would need an additional standard for representing values beyond 0 through 9 and A through Z. We can't fully describe all the numbers in base 64 with the current way we represent large values. We need an extended alphabet. All right, that makes sense? Okay, so a lot of kind of complexy numeric-y things that we talked about today, but all really good stuff. Hopefully, well, a couple different pieces here. Hopefully all of you who have undergrad degrees in something close to the rate of computer science, we've added some things to your knowledge base. I think I probably went into some deeper depth than a lot of undergrad architecture courses might go. For those of you who don't have a background in that, the good news is you've been using numbers your entire life. Now we just need you to compartmentalize that we have different ways of representing numbers when it comes to computing. All right, next class, we're going to start looking at actually writing code in ARM. So some of these things should be familiar to you when you looked into ARM registers and stuff like that. We'll look at some ARM instructions. We'll look at some ARM assembly. But for next class, just to wrap up this discussion, we're going to say, right, I'm going to go, if you want to go beyond 2 pages, you certainly can. All right, but I really want you to look into these different things, fill in any gaps that we maybe didn't talk about in class, and then also get some experience writing. But computer science isn't necessarily a writing intensive thing. So I'm going to still do it as a 2-page paper. I care more about the research you're doing, and then I want you to pick the highlights out of that research, because we'll spend the first couple minutes of the next class talking about that highlight reel of those things. So write a 2-page paper describing the reasons, well, let's say the various uses of binary, octal, and hexadecimal in modern computing. Actually, I'll throw decimal in here too. Decimal and hexadecimal in modern computing. When are these bases used and why? Make sense what I'm asking? So take our discussion today. That should have poured a decent foundation for this stuff. And now go out and give ourselves some examples. So for instance, today we looked at that hexadecimal is often used for representing memory addresses. And we said, why? Because all the memory addresses in a computer are one big long street. We might want to remember a whole bunch of stuff. Okay. And we want to, when we represent, when I want to get to, you know, house number 42 million down the street, I want to be able to say that number in the smallest, most compact way possible. All right. So I'm looking for things like that for you to fill in the blanks in your knowledge. All right. Questions, comments, concerns, bribes. All right. I will see everybody on Monday. I was like, all my online people must be sleeping.